Welcome to our panel discussion. Tonight we will be discussing the viability and practicality of different potential solutions to the problem of acid mine drainage. My name is Chris Ladansky. I'm a second-year geology student, and I have with me Nathaniel Ubana and Patrick Cordero, who are also second-year geology students, and Stuart Merritt, a second-year environmental sciences major. Now, as a bit of background, the EPA states that acid mine drainage is currently the main pollutant of surface water in the mid-Atlantic region. It is essentially a low pH effluent from metallic and coal mines, whether abandoned or still active. The process behind what causes this is complex, but simply stated, mines expose these metal sulfides, primarily pyrite, to the air and water, allowing them to rapidly oxidize, causing an increase in acidity and releasing an assortment of metals. Many of the streams impacted by acid mine drainage have a pH of less than 4, which can be harmful or even lethal for many fish species. In extreme cases, waters from acid mine drainage have been found to reach negative pH values, which is more than enough to ensure all water is nearly inhabitable for all aquatic life. The decreased pH values also have the effect of enhanced dissolution of toxic heavy metals such as zinc, copper, cadmium, lead, chromium, and arsenic. Not only can these metals disrupt metabolic functions, but they can persist for extended periods of time in natural ecosystems, accumulating in successive levels of the biological chain. This makes them hazardous not only to aquatic species, but to humans as well. So acid mine drainage is clearly an issue we need to do something about. And the point of our panel here is to discuss methods as to how we might go about solving it, whether through treatment or prevention. Let's start with Nathaniel. What do you propose might be the ideal method for dealing with this?
Okay, so the idea that I propose to solve the issue of acid mine drainage is a process of using limes to neutralize acidity, which is also referred to as liming.
Okay, and what exactly is liming?
Okay, yeah, so by definition, liming is the addition of substances such as limestone and or calcium carbonate to an acidic body, in this case, the acid drainage. This lime that is added dissolves into calcium, bicarbonate, and hydroxide ions. The hydroxide ions that are produced by this dissolution react with the hydronium ions that are present in the drainage, creating water. Since hydronium ions are responsible for the acidity and therefore lower pH of the drainage, as the hydroxide ions react with the hydronium ions, this would result in the formation of water. Now, since the hydronium is being used in the reaction that is forming water, the hydronium content of the drainage decreases. This decrease in hydronium leads to an increase in the pH of the drainage and therefore slowly decreases the acidity of the drainage effluent, neutralizing it.
Okay, so that deals with the pH of the solution, but how does it solve the problem of the heavy metals in the water?
So in terms of the metals that are contained within the drainage effluent, it is important to note that the solubility of metals is dependent on the pH of the medium, in this case, the drainage. When this ideal pH is not present in the medium, the metals lose solubility and therefore instead precipitate out as minuscule particles. Since the method of liming can control the pH of the drainage, all we need to do to separate the metals from the drainage is bring the pH of the drainage to a value where the metals are insoluble and precipitate out. Some examples of pHs where common minerals become insoluble are around 8.5 to 9.5 for iron, 9 to 9.5 for zinc, and 10 to 10.5 for nickel. Simply looking at the pHs at which these metals become insoluble, we can say that they are relatively close, and so using a pH where all these metals become insoluble, they can be precipitated out of the drainage effluent and filtered out.
Okay, so basically raise the pH and the metals precipitate out. Would this be more of a protective solution or a mitigative solution?
So liming is both protective and mitigative.
And how so?
It can be protective in that the lime can be used to fortify the water's alkalinity, creating a buffer system. This use of liming as a preventative measure is implemented in areas that are more susceptible to acid conditions, like soft water lakes and ponds, which have little buffer capacity and are located in areas that experience large amounts of acid deposition. Now, liming can also be mitigated in the situation where the lake or pond is already acidified. In this instance, the liming is working to recover the body of water and bring it back to safe pH conditions.
Okay, and what reasons make this an ideal method to solve the problem?
In terms of how ideal the solution is, it is appealing due to the fact that, as of now, it is one of the most cost-effective methods available. When you take the cost of neutralization of 663 Adirondack lakes with acid neutralizing capacity ANC values of less than 200 microequivalent per liter, calculations were made using calcium carbonate, and it was found to achieve a range of target levels of ANC for 1, 5, and 10-year periods of base application. The estimated costs for a 5-year base addition program range from $40 to $75 per surface hectare for accessible lakes, and from $450 to $675 per hectare for remote lakes, and this is based on $1982.
Okay, are there any other reasons this might be ideal?
So other reasons as to why the solution is ideal is that since a natural mineral is being used to remedy the problem, we don't have to worry about it harming the aquatic ecosystem of the bodies of water we add them to, both in the short term and long term.
Okay, so liming has the benefit of raising pH to safe levels, which in turn precipitates out the metals in solution.
Mhm.
And it also doesn't harm the aquatic ecosystem. So how would we go about applying the solution? Maybe Stu, you have some insight?
Well, acid mine drainage is generally grouped into two categories, and that would be passive and active systems. The main objective of these treatment methods is to lower acidity by generating alkalinity and reducing both toxic metals and sulfate concentrations in the affected water. Both systems have their advantages, and it's important to understand the strengths of each one relative to the chemistry of the contaminated water we're dealing with. In active systems, we introduce neutralizing chemicals such as lime, calcium carbonate, sodium hydroxide, and magnesium oxide to raise pH levels, accelerate oxidation of iron, and precipitate out metals such as hydroxides and carbonates.
So basically like the type of treatment that Daniel was explaining.
Exactly. And in passive systems, it's more suited for mine effluents with lower acidity and lower flow rates. Treatment involves chemical, biological, and physical methods to reduce contaminant levels. Alkaline components added to the system aid in neutralizing acidity, while organic substrates precipitate out unwanted metals through reduction.
Would there be a better system to use, active or passive?
It's entirely situational. Each system has its advantages relative to the mine drainage you're dealing with. From a monetary perspective, passive systems run lower operation costs and do not require as much maintenance. Active systems need additional chemical reagents added, initial mechanical systems introduced into the system, and human labor to ensure functionality of the system. Furthermore, we can group acid mine drainage treatments into the use of abiotic or biological systems, essentially treating the wastewater with or without aid from biological factors. Often, the use of both combines for an effective treatment, but it's not always required in each case. Some abiotic treatments include limestone ponds, limestone channels, anoxic limestone drains. These systems are all relatively the same speaking from a geochemical perspective, however, they're slightly different in application. They apply the chemical reactions that were mentioned earlier when Nathaniel was talking about his liming. Biological treatments are advantageous in the fact they require low construction cost and are low maintenance, showing strong efficiency in treatment. They work by generating alkalinity and immobilizing metals. Specifically, microbes treat effluent by sulfate reduction, ammonification, denitrification, and methanogenesis.
Okay, what are some of the biological treatment methods and how do we implement them?
Well, there's quite a few, and I can discuss a few in detail. We can use a permeable reactive barrier, which is essentially a trench filled with limestone and organic matter, which reduces sulfates and precipitates out sulfides and raises pH levels. They also promote sulfate reducing bacteria and cover all bases for mine contaminated waters. Another effective treatment is the use of wetland environments, which is pretty common around the world. And these can be both natural or artificial environments. They prove to be extremely effective in treating acid mine effluent in both aerobic and anaerobic conditions. Aerobic wetlands can filter and remove particulate metals and are best suited for alkaline mine waters, where anaerobic wetlands utilize submerged substrates such as limestone and organic matter for neutralizing of acidic waters, sulfate reduction, and the transformation of ferric oxide to ferrous oxide. These anaerobic wetlands are best suited for metal-rich and net acidic mine effluent conditions. Lastly, we can discuss bioreactors, which are a manufactured system promoting a biologically active environment. They are generally passive systems that treat effluent through biodegradation with the use of microbes. They depend on chemical composition of acid mine drainage, electron donors and receptors, temperature, and pH. Unfortunately, this system is beyond the scope of this discussion and somewhat lacks geochemical relevance, although it is a very important method in treating acid mine drainage. Any of the mentioned methods above are proven effective in treatment of mine effluent and been implemented all across the world. It is important to understand both from a biological and geochemical perspective the effects of acid mine drainage and the necessary remediation techniques to reduce the risk on the surrounding environment. Okay.
And can you tell me just how effective these remediation efforts are in treating the acid mine effluent?
For sure. Well, a case study in Canada, actually in Sudbury, Ontario, utilized the permeable reactive barrier technique. And in 1995, it was implemented downstream from an aquifer of a mine. Sand, wood chips, compost, limestone, and gravel were designed as the reactive layer and encouraged reducing bacteria to populate. This increased pH from around 4 to about 7, reduced copper and nickel 300-fold in its reduction, and effectively encouraged sulfate reducing bacteria to populate by 400,000%. This is a cost-effective, easily implementable solution and has been proven to work.
Okay, so these are solutions that seem very effective and will help with areas already affected by the acid mine drainage. But how might we go about the prevention of it in the first place? Patrick, maybe you can shed some light here?
Yeah, for sure. So there are two different approaches to preventing acid mine drainage and that are most commonly used. One is preventing exposure of mine materials, known as tailings, to oxygen and flowing water, which carries dissolved oxygen, and preventing bacteria from catalyzing necessary actions to take place for acid mine drainage to occur.
Okay, and how would we go about this?
Yeah, so one popular method is disposing mine waste underwater through a method called deep sea tailings or submarine tailings disposal. This entails mining waste being dumped into a pipe that goes deep into the layers of the sea where sunlight that drives photosynthesis is not interfered with, as well as corresponding aquatic ecosystems. Another popular method is surface water diversion. This uses safeguarding pipes, waterproof channels, and altering slopes around the material area to prevent the production of acid effluents from the mine. It goes without saying that these two water-based processes should be used in conjunction with rigorous and accurate hydrogeological and hydrological studies. Other miscellaneous prevention approaches include flooding abandoned mines with water, which removes the oxygen necessary to form acid mine drainage, or fill mines with alkaline materials to prevent acidic water from forming. Soil compaction, which as its name suggests, is the compaction of material with the aim of decreasing mine waste permeability. This approach helps in two ways. First, it reduces potential water flow to mining materials, which lessens the chance of oxidization of sulfides. And two, it decreases oxygen diffusion, which makes the area less habitable for bacteria that catalyze acid mine drainage reactions. And lastly, the application of chemicals that interact with mine materials to reduce the release of acid, iron, and other heavy metals into reservoirs. An example of this would be placing a lime layer near the materials to achieve alkaline environment, which stops acidic proliferation.
Okay, so that solution would kind of go hand in hand with what Nathaniel and Stu were talking about, but more in a preventative sense.
Yep, exactly.
Okay, so we've heard from 3 exceptionally skilled professionals about methods that could be used to treat the problem of acid mine drainage, whether it be by treatment methods or methods of prevention. Introducing lime into a contaminated area can raise the pH and precipitate out dangerous heavy metals, while biological treatments offer advantages in cost and maintenance that make it more viable and economical. Of course, we also need to consider the preventative measures that must be taken in order to ensure that future mine waste doesn't contaminate any ecosystems, essentially by preventing the waste from being oxidized in the first place or by preventing it from coming into contact with catalyzing bacteria. All these methods show promise and should be considered for future remediation and prevention efforts. Thank you for joining us in this panel discussion.